right, so the last thing we're going to talk about is how to determine whether or not a molecule is polar, right? So we talked about bond polarity at the very beginning of this week, the very beginning of this chapter. And that was how we can tell using electronegativities how polar a bond is, right? Now we want to know about whether or not a molecule is polar, which means we're going to have to incorporate the geometry information that we learned about in the last two lectures. Okay, so first of all, a molecule has to consist of polar bonds in order to be a polar molecule, right? So for example, something like you have something like this would be the correct Lewis structure for chlorine, the chlorine molecule. However, this is a non-polar bond because they're the same identity. And so this is definitely not going to be a polar compound. Okay, you have to consist of polar bonds to be a polar molecule. So this is definitely not going to be a polar molecule. All right, but now let's think about molecules that are made up of polar bonds, because that's actually most of our molecules. So this is CH4 right here. Carbon is more electronegative than hydrogen, so each one of these bonds is polar, where if we're sort of drawing our arrows that point towards the more polar species, it would look like this, right? But because of the symmetry of this molecule, because there are four groups and they're all identical, all of these dipoles, what are called dipoles, all of these little arrows that we can draw showing the polarity, will actually all cancel out, right? Since carbon is bound to four identical groups, it doesn't matter that those bonds are polar. So this molecule has polar bonds, but because of its symmetry, because all four of those things are the same, it is a non-polar molecule. Okay. However, if all of a sudden we have, this is Ch3Cl, so this is a chlorine atom, and these are all hydrogens. Now it has this sort of unequal distribution of electrons where yes, these three groups are pointed in this direction, but this last group is now pointed in a different direction. So when we sum up all those arrows, what are called dipole vectors, and don't really worry about it because you guys don't know vectors yet until you get to like Calc 3 or something like that, but that's the fancy name of what they're called. They're basically arrows in space. They won't sum up to zero. So what does that mean? So what's the difference between a non-polar molecule? So for example, methane, we said was a non-polar molecule, even though it had polar bonds, versus this is now a polar molecule. Right, so what does that mean? It means that if we looked at the electron density in this structure, we would see that this region here, right by the chlorine, has high electron density compared to this region back here, which has relatively, this bottom part here, which has relatively low electron density. So just like when we were talking about polar bonds and how that for a bond to be polar, there was an unequal distribution of electrons. A polar molecule is the same idea. It means that one portion of this molecule has more electron density than the other portion of this molecule, right? If we have a polar molecule, or I'm sorry, if we have a non-polar molecule, the electron density is evenly spread throughout. So there's no region of high electron density. There's no region of low electron density. Actually, make it sort of a color in the middle. All the electron density around this molecule is equal. Equal electron density throughout the molecule. Okay. So how do we spot polar molecules versus non-polar molecules? Again, it's going to have everything to do with the geometry. Okay, if all the bonds in a molecule are the same, even if they're polar bonds, if they're all the same, then they'll all cancel each other out, right? They're all distributed equally in all directions. Even if they are polar bonds, those bonds will all sort of cancel each other out and lead to a non-polar molecule. If one or more of the bonds is different, so for example, this one was chlorine and these ones were hydrogen, that will lead to the molecule being polar. And then lastly, if there are lone pairs on the central atom, that will also make it so that these dipole vectors don't cancel out. And so those molecules will also be polar, right? So in this case here, I have these two arrows pointing towards that electronegative oxygen. There's on the other side are lone pairs, so they don't get canceled out. And so water would be an example of a polar molecule. All right, so this is how you can tell pretty easily whether a molecule is going to be polar or nonpolar. If all the bonding regions are the same, it's nonpolar. If one or more is different, it will be polar. And if there are lone pairs on that central atom, it will also be polar. Okay, so let's do these with these two examples here, boron trichloride and arsenic trichloride. What I'm actually going to have to do is make sure to have a periodic table handy. All right, so step one is going to be to draw the Lewis dot structure of these two compounds. So first I'm going to make some space for myself. White out all that noise. Okay, so BCl3, let's calculate the number of the number of valence electrons that are in this molecule total. So I'm going to number my columns 1, 2, skip the transition metals 3, 4, 5, 6, 7, 8. So boron has 3 and chlorine has 7. So this would be 3 plus 3 times 7 gives me a total of, gives me a total of 24 for the boron trichloride. So I'm going to put my less electronegative atom in the middle. That's the boron. So I'm going to kind of go through this quick. This goes back to these Lewis structure lectures. So make sure that you guys have that down. Decorate the constituents. Draw single bonds. Subtract that from my total. That would be subtracting 9 from 24, which would leave me with, I'm sorry, not 9. I can't count. Subtract 6 from my 24, which would leave me with 18. Now I'm going to make sure that the octet of all my constituents are taken care of. So that's 1, 2, 3, 4, 5, 6. Okay, and then the last step is to check and make sure everybody's octet rule is satisfied. Boron, remember, is one of those exceptions where it only wants 6 electrons to complete its octet. So actually everybody here is perfectly satisfied. Okay, here I have a trigonal planar because of my 1, 2, 3 electron regions. And that's both the electron geometry and the molecular geometry. Because all 3 of these groups are the same, they're all chlorines, and my central atom does not have any lone pairs, this molecule right here would be non-polar. All right, it sort of meets this rule right here. All the bonding regions are the same. All right, now let's do arsenic trichloride. Go to our periodic table. Arsenic lives down here, so it has 5 valence electrons. Oh yeah, so now I have 5 plus the 3 times the 7 on the chlorine gives me 26. Put the less electronegative atom in the middle, that's the arsenic. Put the chlorines around it. Single bonds, 2, 4, 6. That takes me down to 20. I complete the octet on everything. All the constituents. So that leaves me, that was 18 that I just put down. So that leaves me with 2. And what happens when I have any that remain? They go on the central atom. Okay. Now my electron geometry, because I have 1, 2, 3, 4 electron regions, the electron geometry, I'm going to be shorthanded and just write EG for electron geometry, is tetrahedral. But one of those is occupied by a lone pair. So the molecular geometry is going to be a trigonal pyramidal. And because that central atom has a lone pair, this molecule will be polar. Okay, so that's the procedure of how you would go about, just given a molecular formula, how you would go about determining whether a molecule was polar or non-polar. Again, it has to do with these 3 rules right here. If all the bonding regions are occupied by the same type of element, it's non-polar. If one of them is different, then it will be polar. Or if there's lone pairs on the central atom, that will also make it polar.